Okay, sorry about that. The barking dogs have been the bane of my video making. Anyway, so back here, the cross tabulation. So on a test, expect to create one of these and then do a chi-squared test on it. That's kind of how it works. So I'll give you some data. You'll have to do a cross tabulation of a bivariate cross tabulation. Create the table, get the cells, get the marginals, and then do the chi-squared test to see if it's a significant relationship. Keep in mind the marginals, right? So if you look here, the cells are what's obvious. So there's 600 of the here's the total sample, 4,620. Of those 4,620 people, 691 of them are men first generation, 1,259 are men non-first. And then, so the cells are the actual counts, whereas the marginals are the sums of the rows and the columns. So this first row marginal here, this is just the total number of first generation students, right? This number here is just the total number of second generation. Zoom back in a little bit so you can see that, right? So this is non-first men, non-first women, total non-first. And then this number would just be the total number of women, total number of men. So remember, those are called the marginals, and those come into play in the calculation for chi-squared. Okay. So again, how do we know if there's a real statistically significant relationship between our independent and dependent variable? It's not the fifth generation, it's going to be the first. So the independent variable being sex and the dependent variable being generation of college students. So the first thing that we do with a chi-squared test is we calculate what it would look like if there were no differences at all. So we calculate, it's almost a, what's the word for it? Like a hypothetical cross tabulation that we would expect to find if we expected no relationship at all. So we have, this is what we observe. Right? This is what we found in the real world with our sample. We took a sample, did the cross tab, and then we're going to create what's called an expected frequency. And the expected frequency, like I said, is what we would expect if there was absolutely no relationship. So what we would expect would be essentially that there's no differences, right? So we have that obviously our columns are always adding up to 100, but men and women have the same percentage of first and non-first. So this is what if we hypothetically created an example where there is no relationship at all, this is what it would look like. And hopefully you're asking, how did I calculate this? And I'm going to show you here in a second. So, but basically this chi-square thing comes down to comparing what we actually observe to what we'd expect if there was no association at all. Okay, so kind of to the, so what main definition of the day. The chi-squared test is an inferential test designed to test for the significant relationship between two nominal or ordinal variables organized on a bivariate table. Exactly what I've been talking about. So looking at, taking a bivariate table and testing to see, is the relationship between generation status and sex significant? Or can we not be, sure with any degree of certainty that it is significant? And another thing, it's the chi-squared test, not chi. So don't, when we talk about, doing a chi-squared test, chi is a type of tea. So just, just so you can say it the right way. I went to graduate school with a guy who just refused to say chi. He always called it the chi-squared test, and it kind of annoyed me. So, yeah, it'd be nice to say it right. But yeah, so it's so the chi-squared test. So another definition that we'll want to make sure that you're clear on is what does it mean, statistical independence? So statistical independence means that there's no association between the two variables. Essentially, that the distribution of the dependent variables within each category, the independent variable, are identical, as in here. See, the distribution, the percentage distribution of the dependent variable within each category, the independent are identical. So within the independent variable category, sex, men and women, the distribution of first is equal, the distribution of non-first is also equal. Okay? So independence means they're not related, dependence means they are related, and we can only say that they're dependent based on the chi-squared test. Okay, so hypothesis testing with the chi-squared test, kind of similar to hypothesis testing before in the sense of you're going to have a pretty standardized procedure. We got to have make assumptions, state the hypotheses, and select alpha, select the sampling distribution, specify the test statistic, compute the test statistic, and then make a decision. So the first thing is making the assumptions. You don't have to make any assumptions about the shape of the population distribution. Unlike the stuff with the hypothesis testing where we used either a Z distribution or a T distribution, I'm going to show you today that we're going to use a different distribution. It's the chi-square distribution. It does not make any kind of assumptions, or it doesn't rely on a normal distribution or any kind of spread. So it's a lot more flexible. We don't have to have, it could be very skewed, it could be normal, it could be, bimodal. The point is that we don't make any assumptions about the shape of the population distribution. What we do, obviously, with any inferential statistics, you have to assume random sampling. So the sample, the data was collected via random sampling. Okay, and then lastly, that they're measured at the nominal or ordinal level. So those are the assumptions of the chi-squared test. The null and research hypothesis are going to be relatively straightforward. They'll always be the same. Your null hypothesis will be that there's no association between the two variables, and your research hypothesis will be that there is a relationship, that they're related, that they are this is a mistake, sorry about that. Statistically independent. So if they're statistically independent, so the research hypothesis states that they're statistically independent of one another. They don't, they're not reliant, there is no association. The research hypothesis is that they're statistically dependent on one another, that they are related, that there is an association. So when you're writing this stuff out, just make your null hypothesis that there's no association between, full of typos. There's no association between first generation college students and sex, and then the research hypothesis that there is a relationship between the two variables. So that'll always be the same now. There is not a relationship, there is a relationship, and then just spell out the two variables that you're looking at. In this case, it's generational status of college attendance and sex. Okay. The last little bit before we get into the example, this is how your book uses this notation as well, so I want to be consistent, but the expected versus the observed frequencies. So I talked about before, the expected frequencies are kind of what we would expect if there was no relationship. Basically, if the two variables were statistically independent. Essentially, it's like, what is the, what would the bivariate table look like if the null hypothesis were true? The observed frequencies are what we see. There's no calculation there, that's just what you observe. And like I said, the decision of whether to go with the null or research hypothesis comes down to what the difference between the expected and observed is. So you compare these two things. Okay? So expected frequencies, we're going to have to calculate that. Observed frequencies, there is no calculation. It just is, it is what the data shows. So this is what we collected. This is the observed frequencies. Okay? So expected are a little bit different. We have to calculate that. The calculation is relatively straightforward. It's easy to make a mistake here, so I suggest writing things out. But just be cautious. I'll show you where the mistake can be made and where I've seen it in the past. Like I said, the difference between the expected and observed frequencies determine the likelihood that the null hypothesis is true, and that the variables are in fact statistically independent. Okay, so our decision of whether to go with the null or research hypothesis always comes down to comparing these two. And the first thing we do is we calculate these expected frequencies. So the equation here is the expected frequency is equal to the column marginal times the row marginal divided by n. So let's go back here and take a look. So like I said, they're based on frequencies, not percents. Key point number one. Don't use the percentages, use the frequencies, okay? So if you look here, we've got, this is our F observed, right? Our frequencies that we observed right here, this is the table. We want to compare it to a frequencies expected, but we got to create that first. So go back here to the equation. It's the column marginal times the row marginal divided by n, okay? So when we want to calculate the expected frequency for men, we take the row marginal times the column marginal divided by n. So let's kind of hit that hard again here. So in order to calculate the expected frequency of men first generation, we would take the row marginal times the column marginal divided by n. Now here's the check for understanding question. When we want to calculate the expected number of women who are first generation college students, we use the same column marginal as we did for men, right? It is the same column. We just use a different row marginal. So let me show you how that's calculated out. Oops. Okay. So to calculate, again, wrong table. This is the observed number of first generation men and women. I'm sorry, the observed number of first generation college student men, the observed number of first generation college students who are women. So that's the F observed. We're done. What we need to get is the F expected. So in order to get the expected frequency for male first generation, we take the column marginal times the row marginal. So we'd have 1950 times 1936. Oops. 1950 times 1936. And then divide by our sample size, right? So we take the column marginal times the row marginal divided by n, 4,620. So we'll divide that number by 4,620, and we get 817.14. It's not going to really matter if you round that down, especially since, think about it, we're talking about people. So obviously we can't have 0.14 of a person. But it might be wise just to, when you're doing the expected frequencies, I wouldn't round too early, though it's really not going to make a huge difference. So if you want to round that to 817, that's totally fine. But if you want to put 817.14 in, that's also fine. It's not going to make a huge difference, but just so I can be consistent with your book, here's that 817.14. So basically these are the expected frequencies for men first generation, men second generation, men non-first, women first, women non-first. So this number came from the calculation of the row marginal times the column marginal divided by n. So let's just do another one. Take a look at this. So this is the expected number, if there were no relationship, the expected number of women who are non-first generation, 1551.14. So let's just calculate that number so you can see where that's coming from. So it was the expected number of women non-first. So we'd have to take the row marginal, which would be right here, right? So here's the row marginal for non-first and then the row marginal for women. So it's 2,684 times 2,670. 2,684 times 2,670. Right? And then we divide that by the total, which was, I wish I could remember, 4,620, yeah. 4,620. Okay, 1551.14. And then if you go back down to your expected frequencies here, there's that number right there. So what you're going to do is you're going to have a table of observed frequencies. You're going to have to recreate the table of expected frequencies. So basically what this is saying is that if there were no relationship, we'd expect about 817 men in our sample to be first-generation college students. And if you look here, we have 691. So we'd expect there to be more men first-generation students than there are if there were no relationship. That's sort of what's going on here. The last thing I want to point out, and this is one of those places I always like to, add in a check to see if you've, like little checks to see if you're on the right track, if you've made an error. You should always get the same row and column marginals for the expected frequencies that you did for the observed. And it makes sense because the expected frequencies are based on the observed row and column marginals. So if that's the case, you'd expect those to be the same. So basically, when you look at your observed, keep going to that one. Look at the observed, 691 men first, 1259 men non-first. You add those up, 1950. You'll get the exact same marginals in your expected frequencies. So that'll be a way to check and make sure you've done the right calculations, make sure you get the same marginals. The cells will be different, but the marginals will always be the same. Okay? So that's it as far as how to obtain the expected frequencies. So now that you've done that, you've kind of done the hard part. Now it's just sort of plug and go. So here's the equation to calculate chi-squared. There's a little, there's chi-squared. And chi-squared is equal to, this is a little blurry. Let's see if I can enlarge that a little bit, or if it's just, I might just have low definition. Yeah, it's just kind of low definition. Sorry about that. But chi-squared is equal to the sum of, and this is obviously, it's in your book, and I have it. I've posted a formula sheet for you guys on BlazeView, so if you forget the formulas or can't find it in the book, the formula sheet's up there, so you should be able to look up the formula if you can't find it. It's the sum of the observed minus the expected frequency squared divided by the expected frequency. So F observed minus F expected squared divided by F expected. Okay, so let's put these two, let's put this up on the screen. Again, this is from your book. So hopefully, if you have, if you have questions, you can see it worked out in the book as well. Okay, so take a look here. So here's men and women in terms of observe, expected, observe, expected, okay? So we observed 691 men who were first generation and 1259 men who were non-first. And that came right from here, 691, 1259, that's the observed. Same thing with the observed for women, 1245 first, 1425 non-first, okay? So the first thing you want to do is put in a column, just make a, you don't have to draw it out exactly like this, but it would be nice because, you can check and you can make sure here's your marginals right here. There's your total. You can, again, you make sure everything kind of is lining up. But you're able to compare how many men first you observed and how many you expected, how many men non-first you observed, how many you expected. So what this is telling me is that we observed less first-generation men than we would expect given no relationship, and we observed more we observed more non-first-generation men than we would expect. Same thing with the women, but it's the opposite. We expected less first generation women than we observed, right? So we observed this many women who were first generation, but we'd expect this number if there was no relationship, which means that we have a surplus of first generation women and a deficit of first generation men, meaning that you should start to think that maybe there's a relationship here because, you know, we're expecting more here and expecting less here for women. Okay. So this is the table you want to set up. And if you think back to remember when we calculated standard deviations, that's kind of what this looks like here. So I drew this out, but I think it might be easier just for me to walk through here rather than writing it out. I have it written out, but let's just show it on the screen. If it's not working, I can try something else. Okay. So the first thing you want to set up is your column for the observed. So men first, men non-first, women first, women non-first. This is what we observed. This isn't any surprise here. It's just this is the data we gathered. And then here's the expected frequencies, right? This is what you calculated. There's that 817 and that 1551 that we calculated. But here's your expected, here's your observed. And if you go back to the chi-squared, it should sort of look like the calculation of the standard deviation to you, slightly. Obviously, I mean, they're not really related, but I think that in terms of the formula, it looks similar. And in terms of the calculation, I want you to do it similarly in terms of kind of building. So we're trying to get this number here, right? The sum of all the observed minus expected frequencies squared divided by the frequency, the expected frequencies. You can't do this without building up into pieces. So it's like we first need, you know, the observed and the expected, and then we subtract them, and then we square them, and then we divide by the expected, and then you sum it all up. Again, it's kind of, like I said, it should really remind you of the calculation of the standard deviation. Go back and look at how I did the same kind of thing where I kind of walk you through it. This is exactly how it'll be on the homework, on the exam, where I'll give you these columns. I'll set you up to, I'll set you up to do it, but you got to know where these